Okay, so sorry. In this video, we will be we'll be answering a few problems on the applications of first and second law of thermodynamics. Okay, so there are um, there are categories in what kinds of problems you will be encountering rather. They are simply categorized as follows. So we have two types basically of thermodynamic systems. We have the closed system. This is in other words called the control mass or CM, no? And we have what is called the open system. Open system, in other words called the control volume or CV. For the closed system, uh, basically what happens here is only energy change, no? Or rather energy transfer. That's the more appropriate word. Only energy transfer. So we can only see here also state change. No? So state change, namely expansion, the opposite of it, which is compression, uh, whether energy is absorbed or the opposite, released. Okay, so that's for closed system. For open system, not only energy is transferred, no, also mass. There is another system aside from these two. We call that the isolated system. In that case, there is no transfer at all, both energy and mass. Yeah, so hence the word isolated. But we're not going to focus on that. For open system, so yeah, there is energy and mass transfer. We have, if it's open system, you have to note, as early as now, I'll be saying this, the work involved here is shaft work, no? Or just simply WS. Or I think this is better, no? Because eventually later, W sub S could also mean isentropic work. Isentropic as in automatically the process is assumed as adiabatic. That is, the heat transfer, or Q, is equal to 0. We'll be having that later on. My point is, this could also mean isentropic work. So, yeah, just try not to get confused in that sense. So, yeah, shaft work is involved for open system. At the same time, in the same sense, the work involved in a closed system is called boundary work. So what is an example of a closed system? We have a piston cylinder assembly. So in this scenario, you will have initial pressure, final pressure, and a certain pressure that would be needed to make a change, no, in the system itself. Let's call this. There's a term for that. I can't remember at the moment. Let me consult my notes. Yes. Pressure to, for example, lift. No. Yeah. We'll just call this P lift. So yes. Yeah. Piston cylinder assembly is an example of a closed system. In an open system, so with the idea that shaft work is involved, in this case, you will encounter quite a lot, no, of thermodynamic devices. They either use shaft work or they don't. But essentially, these devices, basically they're associated with open system. No? So we have devices with shaft work or without shaft work. So there are only 4 devices no, that have shaft work. We have the compressor, we have the pump. Both of these, they require minimum work. No? So typically in problems involving these devices, it is possible that you'll be asked to find the minimum work required, since these two devices, I think they consume shaft work. Let me verify that. And the other two consume shaft work. Sorry, produce rather. Yes, so compressor and pump consume uh, to function, no? Consume shaft work. We have the turbine, and the expander. Expander is basically a turbine, just for a more specific function. Both of these guys, they consume shaft work in order to function. So, sorry, consume use. Use is interchanged with consume. These two guys, they produce shaft work, and typically for that, for those two devices, we are tasked to compute for the maximum work, no, maximum shaft work. Essentially, whether the work is maximum or minimum, it is under the assumption that the process is reversible. Uh, Process is reversible. Yeah, since we are calculating for the maximum possible work that could be produced, no, by the device, or the least work that could be consumed by these two guys, compressor and pump. So, in other words, reversible work, aside from being called minimum or maximum work, they could also be called ideal work or isentropic work. There are a lot of similar names, no? Other names for the same thing. So just have to take note of that. What else? Okay. As soon as possible, I'd like to go to a certain problem already, so we can apply what I've been discussing. No, we'll have that later. Aside from thermodynamic devices with or without shaft work, we have steady state, steady state processes, or just SS. In this case, it is important to note that there is no accumulation. For unsteady state process, or in other words called transient state, this is where accumulation is involved, no, or happens. So yeah, an example of a transient system is a closed system that is exposed to an open system. So that's possible. Although notably for transient state, it's one notable example is when you have a scenario where tank is being filled or being emptied. So you have a line like that, and then you have a valve that's connected to a tank. So that's gonna be your state one. So typically this could be your first tank, or your tank at state one could be evacuated. That means empty. In that case, you're lucky because the computations for that kind of problem is gonna be pretty simple. But it's also possible that there is already gas inside the tank, so that makes your solution pretty long. No. So yeah, for a time, you have a certain pressure and temperature. Here you only have a pressure. You have a certain gas, and until it reaches a certain pressure, let's say 1.4 megapascals, that's the only time that you close the valve. No? So these kinds of problems, automatically it's transient state. Okay? So we have that. we also have, basically the coverage for this video is just going to be non-reactive systems. No? Reactive systems such as heat effects, that's gonna be for another time. So, okay, it's important to point out that for our lectures on thermodynamics, the references will be Smith et al. And Sontag. Sontag uh, for the thermodynamic tables. So yeah, in Smith et al., it's important to take note of page 266. There, wait, what edition is this? Might be a different if you are using an edition that is not the same as mine. Let me check what edition mine is. This is 8th edition. Okay. Okay, so page 266 gives you the equations of balance. No, in every problem, you have to first set up your law of conservation of mass. This is your material balance. Your first law of thermodynamics. This is your energy balance. Also, if applicable, your second law of thermodynamics, that is your entropy balance. So for law of conservation of mass, for reference, for steady state processes, typically it's just M1 equals M2 equals M. Then you put SS. For transient state, that's slightly more complicated, no? M1 plus Mi equals M2 plus Me. So in this case, the transient, the tank filling problem, I means inlet, E means exit, no? So your inlet state is this one. This is your exit state. Your state 1 is this one, no? The one inside the tank. And then state 2, what happens to the tank after a certain process has been achieved, no? So in that case, I'll give you insight already. Again, this is for transient state TS. M sub 1 rather, because state 1. This one's inlet. Inlet corresponds to I. Okay? So M sub 1 is equal to 0 if this tank is initially evacuated. Also, not M2, ME, the exit, mass exit, is equal to 0 if there is no output stream or nothing comes out, no? In this problem, yes, ME is equal to 0 since evidently there is no output stream, no? Nothing comes out, so yeah. Okay, that is for the law of conservation of mass, the LCM. Also, I'll give you an insight. For example, you have, you're given the volume of the tank. Let's try this transient example again. So typically also you could be given the volume of the tank. It doesn't tell you the volume of the gas inside, but just the volume of the tank. So since we're using the same tank in both state 1 and state 2, yeah, the volume of the tank is just the same regardless of what happens, no? It is a rigid vessel after all. So for example, volume of tank is 0.6 meter cube. You are also given an initial mass of 1.6 kilograms. One technique that you could look into in your problem is to find the specific volume rather. Specific volume has units of meter cube per kilogram, that is volume divided by mass. Volume, in this case 0.6 divided by 1.6, you'll have a specific volume 0.375. This detail could be used for further computations. No? We'll have actual examples where we demonstrate that. You don't have to worry about that for now. I'm just trying to point it out, because usually those are the ideas that you should think of. Otherwise, you'd be stuck. No, from experience. You have a mass, you have the volume of the tank. Why not find a specific volume and see what you could find after that? No? So there's going to be a lot of those things in problems involving applications of first and second law thermodynamics. Okay, so energy balance. So it's different, no? Notably, what I want to point out is let's start first with closed system. For closed system, delta U equals Q plus W. This is typically the case. Also, don't forget, this is steady state. If it were transient or unsteady state, you have accumulation, no? Somewhere there. Please refer to page 266, no, of Smith. You'll see what I mean. The very first term in the general equation of balance is the accumulation. That is only applicable if your state is transient. Right now it's steady state, so no accumulation. You don't have to account for that. Okay, so that is for closed system. For open system, also steady state assuming, then it's gonna be change in enthalpy. Notice, you have to memorize this. Understand. Closed system, internal energy change. Open system, enthalpy change. Okay? Also, these equations are under the assumption or understanding that the work is equal to negative PdV. Don't forget the negative sign. Okay? So technically, delta U is equal to Q minus P dV. If you want to find the heat transfer, Q, delta U minus P dV, since this is Q is capital, you need a mass flow rate, and then times quantity U sub 2 minus U sub 1 minus P dV. If this was changed as delta U equals Q minus P dV, you're looking for the... By the way, what is this lowercase? How is it different from the uppercase? Capital Q means total heat transfer. Total. No? For small q, this is specific. That's gonna be our notation, by the way. Previously, I showed that specific volume is equal to volume divided by mass. What's the distinction between their shapes? So one is small. This is specific volume. This one is just volume. Okay? In the same way, or volume or total volume, yeah. In the same way, total heat transfer is capital Q. Small q is specific heat transfer. I hope that is clarified. Okay? So, okay. Same thing. What's the... Wait. Transpose PdV to the other side. This becomes plus. Okay? Yeah. Okay, so notice the difference. This one has a has a mass flow rate. This one has none. How is that so? Q is in kilojoules, no? Q has units of kilojoule or kilopascal meter cube. Kilojoule, so Q is equal to M mass flow rate tapos that one, no? What is the unit for mass? Kilogram. What's the unit for, ignore the flow rate in the meantime. Delta U, so internal energy is kilojoule per kilogram. Notice how the units cancel. What you're left is kilojoule. That is the unit of total heat transfer. How about for specific heat transfer? Kilojoule per kilogram. That is the unit, no? Specific eh. That's the idea. If a certain value is, or in this case, if the heat transfer is specific, then it has to be per mass, no? Per unit mass, in this case, kilogram, per kilogram. So we established that the unit for internal energy, specific internal energy, since this is lowercase, is kilojoule per kilogram. In the other side, also kilojoule per kilogram. How about PDV? How is it the same unit as the rest in the equation? Let's go back here. So PDV is, pressure is kilopascal, no? And then volume is meter cube. I just wrote it a while ago. That's exactly equal to kilojoule. Same idea here. Okay? I hope the dimensional analysis here is clear, no? So yeah, that is for closed system, open system. That's I'm not saying that these energy balances are gonna be applicable in every scenario. This is just in general, or basically under the assumption that the process is steady state, and also under the assumption that kinetic energy is negligible as well as potential energy. Okay? What if the process is adiabatic? It says in the given that it's adiabatic. Adiabatic, Q is 0. So in that case, for closed system, change in internal energy is equal to the work, simply. No? For open system, change in enthalpy is simply just the work. For adiabatic, no? So yeah, the energy balance is really specific according to the conditions stated in the problem and assumptions you can safely make. No? We're also going to encounter or discuss the normal assumptions, no? Typically. Actually, for kinetic and potential energy, you will assume them as negligible if there is no information about the velocities, about elevation, no? So yeah. For entropy balance, typically if you encounter a problem involving efficiency, isentropic efficiency, for specifically for devices, efficiency for compressor, for pump, what else? For nozzle, and for turbine. So in the exam, we're allowed to have the Smith textbook as well as the Sontag thermodynamic tables during the exam, which is 1.5 hours, but I'd rather memorize this personally, yeah, because right now I haven't seen this in the book yet, but it's gonna be part of the exam anyways. And I think in that case, you'll have to memorize. You have no choice. Okay, compressor, recall. Compressor and pump both require or consume consume work. We'll discuss SLT later, or second law of thermodynamics, in other words, the entropy balance. Let's just go here first. You know that entropy balance will be required if your scenario has this involved. No, isentropic efficiency information is given, or you are required to find it. Okay, so isentropic divided by actual. Let me verify if I got it memorized correctly. Isentropic, actual. Okay, yeah. So I got it correctly. Recall, out of these four, compressor, pump, and turbine, those are the devices that where shaft work is involved, no? So in your energy balance, work is not equal to zero for that reason. For open system, no? Isentropic, uh, yeah. So since that is the case, work is involved. Nozzle, note that nozzle is not part of the list, no? It's not written here. So shaft work is not involved. In that case, velocities rather are involved here. So V actual raised to 2 over V isentropic, or S. That's the reason why earlier I said W sub S could also mean isentropic, because here the subscript S means isentropic. Let me verify if that formula is correct. Yup, that is correct. That is for nozzle. For the rest, everything's gonna be in terms of work. So work, compressor C, isentropic, so S, divided by work, compressor actual, so CAC. Okay. Work for the pump, it's gonna be, sorry, what the heck? That came out of nowhere. Pump isentropic PS over work pump actual, so PAC. Okay, so again, compressor and pump both consume work. The work required here is minimum for reversible condition. That means naturally the actual work is gonna be much more, no, than that of the isentropic. Isentropic is the ideal, so as much as possible the smallest, no. So it's connected with the idea that these devices consume shaft work. So for the turbine, this produces shaft work or mechanical work. It's the ideas are similar, okay? Producing shaft work, so the isentropic is gonna be much bigger always, no, than what it actually produces. So isentropic is gonna be at the bottom. That's the logic. So turbine, isentropic, and then turbine actual, TAC. Okay? Okay, so aside from that, there's another relationship that you have to know. When we say isentropic, automatically the process is adiabatic also. Adiabatic. In other words, heat transfer is zero. So what? When we say isentropic, we can also say the enthalpy is equal to CPT. Wait. That's for later. There's something that I have to cover first. Right before saying that. Okay, wait. So, for... Mm, I mean, I can't really just... I'm not sure if there is a proper derivation for this, but by memory, I know that in this case, the isentropic work, that is basically equal to... Oh, wait. Yes. Okay, I got it. Uh, let's go back to this one. Open system. Open system, steady state. This is our energy balance, no? Again, I did mention earlier that the process, isentropic, the word isentropic, this is our condition. I mean, we have it in our problem. It tells you that the process is also adiabatic. That is, the heat transfer is 0. So in your energy balance, in that case, Q is 0, no? Therefore, work is just equal to the change in enthalpy, or delta H. So delta H, H2 minus H1, basically, that's the case. If this is specific work, don't forget to put a mass flow rate. Again, the concept I pointed out earlier, no? But yes, this is not specific work. This is actual work, as in capital W, no? So yeah, from that, H2S minus H1, again, W equals delta H. We're following this, no? And then H2 minus H1. That is the derivation. So, we have that already, no? Yeah. Notice, this one is for actual, H2. For the enthalpy in the second state, that is for isentropic, it's here, no? At the numerator. That's gonna be the case for both compressor and pump. Both of them consume shaft work. Okay? Okay, so for the nozzle, I'm not sure. We'll skip that one. For the turbine, it's just the other way around. So actually it's at the top, so H2 minus H1, and then H2S minus H1 below, where the isentropic is. No? Okay, so that is one render of the formulas, no? In terms of entropy. But we can also express this in terms of temperature, if that is something that we have to look for. Wait, sorry. So this is in terms of enthalpy, no? What if we can only express it in temperature due to limitation of given data? So in that case, we have this relationship, H equals CPT. CPT. So let's start here. CP and then T2S minus T1. I hope you can visualize what I'm doing. CP and then T2 minus T1. Legit the same thing for the pump. Again, since both of them consume work, shaft work. Okay? So, yeah, that's it. Here naman, for the turbine, legit just the inverse. Okay. So after that, notice this could cancel. So what you have left is just this one. No, you just have those. So that's it. I've already derived the formulas for isentropic efficiencies. Let's now move on to second law of thermodynamics, the entropy balance. So typically, you will encounter delta S equals derivative dq over t plus S gen. Or yeah, gen or S sub g, same thing. This is entropy generation. There's a condition. Entropy generation is equal to 0 if the process is reversible. Sg is not equal to 0 if the process is irreversible. Reversible in real life is impossible. At the same time, it's the most desirable kind of process, no? Uh, yeah, that's basically what everything I'm gonna say. Um, what else? I'm gonna derive three more formulas under this. So 3 S gen is equal to delta S, no? Sorry. Let's simplify this one first. So derivative, this is just gonna be Q over T. Yeah? And then plus Sg delta S. If we want to solve for the entropy generation, let's say condition is adiabatic. Why? Why is it adiabatic? Possibly because for example, our substance is air. If the substance is not in our Sontag thermodynamic tables, air being one of them, then we can just simply assume ideal gas. Gas is ideal, rather. So in that case, for ideal gas, the process is adiabatic. Let me verify that. Could be, but because there are times when ideal gas is the same as isentropic condition. Like isentropic compressor is the same thing essentially as ideal compressor. In that kind of context, ideal and isentropic are interchanged, no? But in some cases, they are not the same. And that's one of the most confusing parts, no, of this lesson. You don't know when to believe who and in what circumstance, no? Yeah, let's just say the condition is isentropic. I need a minute. Yeah. Okay. So under the assumption that the process is isentropic, typically I think this is also gonna be a hint when whether you apply entropy balance or not. Yeah. Why did I say that? Because again, isentropic condition is involved if you have details on any of these, no? The isentropic efficiencies. Automatically, you have to whip out or summon your entropy balance. Yes. So, mm, isentropic condition, automatically you have to write down your second law of thermodynamics equation. So, automatically from that idea, Q is zero. There's no heat transfer. Therefore, this entire thing is zero. Therefore, uh, your entropy generation is delta S. This is capital, huh? Capital, so that means there has to be a mass flow rate. Entropy generation was never lowercase. So always take note of that. No? This is always going to be true. Mm, what if... Okay, starting from there, we have this equation. Let me write it in blue. T ds equals... I can't remember. Delta H minus V dP. This is I'm not sure if I'm supposed to memorize this. That's why I'm writing it with emphasis. Also, that's where you start if you have to bring out an equation that you have to derive. No, um, it's gonna make more sense later on. Actually, that's this one, delta S. Let me just show you. Okay, so T delta S. Again, our process is isentropic. Wait. PV, again, ideal gas, the equation of state is PV equals nRT. If the R is going to be a specific gas constant, then that's PV equals RT only. V is equal to RT over P. Okay, so yeah, essentially, since we can assume that air in this scenario is ideal gas, we can safely assume this one. And what's the other one? Yes. For ideal gas, the dH is equal to Cp dt. Also, du, du, that's lowercase u. That's how I would write it. Cv dt. Cv du. Okay, yeah. But this is not going to be needed in our situation right now. Although those are the specific heat capacities, no, the formulas, under the assumption that the gas is ideal. Okay? So, let's substitute. Tds equals Cp dt minus RT over P. By the way, this is supposed to be capital, not specific. That's big. Sorry about that. Let me just write that correction in my formula sheet. Okay, so RT over P times V RT over P, then write dp. Okay, TDS. So if you divide both sides by temperature, Cp and then dT over T minus R times dP over P. Something looks missing. No, nothing's missing. Cp, then the derivative could be rewritten as ln, no? And then T2 minus, over T1 minus R, and then P2 over P1. Yeah. So delta S, that is S2 minus S1, no? Okay, so that is another equation that's gonna be important, no? It comes from here. You could use this to derive the equation that is used to find T2S. So by finding T2S, after finding that, you could then use the isentropic efficiency formula to calculate the efficiency of the process. So how do you do that? There's a condition, no? S2 equals S1. Since isentropic, delta S equals 0. So in that case, 0 is equal to Cp ln T2 over T1 minus R P2 over P1. Okay, then we could bring this to the other side. Cp ln. Wait, sorry. There's supposed to be natural log, no? Because of the D. R ln. Okay. So after that, also here, it's important to take note of two formulas. In your Sontag, where you find the specific gas constants, let me search what page that is. Yeah, page 760. So R, your specific gas constant, is equal to Cp minus Cv. Then K is equal to Cp over Cv. These relationships are important, no? Let me show you. So Cp over R, we want this form in the right side. And then ln P2 over P1. R is Cp over Cv, no? Substitute there. We're just gonna focus on this part. Everything else just leave as is. And then Cp over Cp. Wait. One minus 1 over k. Is that algebraically correct? Sorry. I made a mistake. It's supposed to be R over Cp. That is the goal. Let me emphasize that. So if ever you encounter this problem in your solution, that's when you know also that you're wrong. It has to be R over Cp. R over Cp ln P2 over P1 equals ln T2 over T1. R is Cp minus Cv. Okay. Then, yeah, just, it's basically this. You don't have to, I won't write it again. Then 1 minus Cv over Cp. Again, K is Cp over Cv. So this is 1 over K. No? So K, it's gonna be K minus 1 over K. Then everything else written as is. So what happens now is we want to remove the ln, so apply exponential on both sides. So by logarithmic property, p2 over p1, and then this one becomes an exponent. So k minus 1 over k equals t2 over t1. In this case, sorry, this is supposed to be t2s. So T2s is equal to T1, multiply this to the other side, and then P2 over P1 raised to K minus 1 over K. This is the equation that you will use to calculate for T2s, or temperature 2 under isentropic condition. You will use that so that you can find, so after finding T2s, put it here in the formula. You'll be able to find the isentropic efficiency of that particular device. Okay, tedious, no? You could simply memorize the formulas, but at least for according to my professor's requirement, we have to derive. So derive starting from the balances, whether it's mass balance, the LCM, the energy balance, or the entropy balance. No? So, are we ready to begin with sample problems? How long have we been? Nearly an hour. Wow. Okay. Nearly an hour. At least I was able to discuss the important concepts. No? Before we proceed, I want to make sure if everything has been discussed. At least all possibilities, no? I think this is important to clarify. I made a mistake here. Okay, so compressor and pump both consume work. As a consequence, isentropic numerator, no? Actuals are in the denominator. That's not the only consequence. For turbine, it's the other way around. It produces shaft work. And aside from actual being this time in the numerator and isentropic in the denominator, the positions switch. What do I mean by that? As in H1 minus H2, and then H1 minus H2S. In that case, let's rewrite the entire thing. Cp and then T1 minus T2, and then Cp T1 minus T2S. Sorry. And then cancel. Yeah. That's basically it. For nozzle, again, this is not one of the 4 devices that where shaft work is involved. Therefore, the nozzle, the shaft work for nozzle is equal to 0. In the same way, there's another device that does the opposite of a nozzle. That is the diffuser. Shaft work also 0. Additionally, for a throttle, that's the case, H2. Yeah, that's basically it, I think. To summarize, uh, this is what I've been talking about now. Properties of saturated mixture. There's another formula. This one is in the book, but at this point, just memorize. Specific heat, specific volume, internal energy, enthalpy, entropy. So that of the liquid plus the quality. For saturated mixture, it will always have a quality. As in, it tells you, it's basically a mass fraction. How much vapor is in the mixture, no? Of the vapor liquid mixture, that is the mixture itself. Okay. What else? Let me look at a different page. Okay. Let me show this. Sorry. For these are the assumptions. No, I've written it here. But in the upper part, notice, as I've mentioned earlier, if you're asked to find minimum work, typically this is if the compressor or the pump are involved. No, they are thermodynamic devices with shaft work, compressor and pump. In other words, called the reversible, the ideal, or isentropic work. This is the lowest possible work to operate in the device. For turbine and expander being basically a turbine, but more specific, typically if you're asked to find the maximum work, that's in that case, you can assume that the process is reversible. If entropy generation is involved, in other words, you have entropy balance, entropy generation would therefore be 0 because your process is reversible. No? Okay, so going down here, I've mentioned about these two guys earlier. Assume that kinetic and potential energy changes are negligible. This one if there is no mention of velocity, and this one if there is no mention of elevation. You assume that the work is 0 if the shaft work is not involved. That is for open system. No? If obviously in a closed system, shaft work will not be mentioned, doesn't mean that the work would be 0. In that case, boundary work is the work for closed system. So that's a different case. Here, assume that the gas is ideal if the gas is not in the Sontag table. For example, air. Our example a while ago, that's the reason why, aside from ideal gas assumption, the condition is isentropic. Therefore, we could assume condition is also adiabatic. That is, the heat transfer is equal to 0. So aside from that, we have helium. This is the this is the Sontag table, no? And yeah, basically we have saturated water, CO2, refrigerant R4110, 410A, R134A, nitrogen, methane. What's this? Ammonia, saturated. So those are just the substances in the Sontag table. Anything that isn't in the table is gonna be assumed as gas ideal. Also, Q is 0 if process is adiabatic, no? Or if the Q value is not given. Or there is no mention that heat transfer has occurred. Okay? Okay, what else? Transient processes, this is what I drew earlier, no? State 1, state 2, inlet state, outlet state, the valve, open, close, control surface. Okay? M1 is 0 if the tank 1 is evacuated. M exit is 0 if state 2 has no output stream. I wasn't able to write the FLT for transient process. It's basically this one. One corresponds to the control volume. The other corresponds to the streams. Mehe minus mihi. M2 internal energy 2. M1 internal energy 1. Mu. Okay? So what's the logic in that? Notice that for closed system, earlier I've mentioned that internal energy is the one in your energy balance. That's exactly the point here. Your control volume is the tank itself. So what's only involved here is the internal energy. Enthalpy is involved in the inlet and outlet streams. That is introduced by the time you are in open system scenarios, no? And that's the reason why it's delta H for the energy balance in open systems, as opposed to internal energy being in closed systems. Okay? So, what else? Concept of irreversibility. I don't like this. Yeah, this is the longest. Irreversibility is, in other words, lost work, no? Yeah. I'm gonna make a video on this separately, no? Okay, this one's good. How about this one? Extensive. Just to get your algebra correctly, this is also what I pointed out. Dimensional analysis from earlier. Also here. This is what I also clarified. Open system, change in enthalpy is Q plus W. For closed system, delta U is Q and then plus work being negative PDV. This is only applicable if we can only assume that PE and KE are negligible. Okay, next page. Is there anything else? What is this? There's a lot, bro. There is a lot. Throttling valve. Yes. I also mentioned about this earlier for ideal gas. In U, CVDT, H, CPDT. To find H2S. Yeah, basically that one. It's also emphasized here. What else? Isenthalpic. Entropy change is 0 because entropy does not change. Entropy is constant. Isenthalpic. Enthalpy do not change. What else? There. I also mentioned about this earlier. Work in closed system is boundary work. Work in open system is shaft work. V not constant. These are two scenarios I've noted under closed system. Rigid vessel, that is, V is constant, so dV is 0. Work is PdV, no? Because dV is 0, work is also 0. So yeah, it's as simple as that. Constant pressure process, V not constant. In an isobaric process or constant pressure process, simply why is it this one? There's a derivation for that. Again, another derivation. But essentially, you get the idea. Either way, it's the same thing. If you solve using du minus w or h2 minus h1, it's the same thing. And since q is capital, no, you therefore need mass flow rate, then small h2, small h1. One of the devices where shaft work is not involved is a throttling valve. I did note that there are only 4 devices that involve shaft work, no? So yeah, anything else is without shaft work. So velocities, I hate this personally. Ratio of pipe diameters, such a pain. Volumetric flow rate, that is area times velocity. Yeah, this is the condition earlier. Also here, mass flow rate is density area times velocity. From there, you have this for ideal gas. Then you have this. There's a lot of information. It's kind of overwhelming, you know. Negative Q, that means heat loss. Positive Q, heat gain or heat entering the system. For work, if your work value is negative, then that is work output. If it's positive, then it's work input. Okay, yeah, that's basically it. I think we are ready to solve practice problems already. I got kinda slacked in the part where I'm supposed to discuss irreversibility rather. And in the part where velocities are mentioned. My notation for velocity will be the one that's familiar, no, in electric circuits. So just to make a distinction, this is specific volume. this is volume, this is velocity. As in the one for, that means voltage in the context of electric circuits, no? Voltage, sorry, velocity. Okay, I'll end the video here. The next video will be about practice problems. Capish? Sorry, that's not goodbye. Ciao, I guess. Bye-bye.